All right, we're back here for the second part of 3.3, and we did some transforming with power models. This time we're going to do it with some logarithms instead. So when transforming data, follow a power model. What if we don't know? It should be squared, cubed, whatever it should be. So there's kind of a solution to that, and a scatter plot of logarithms of both variables should produce a linear. So if you take the log of both of those, you should see that. Now, here's the explanation why. So let's start off with a power model. If I take the log of both sides, remember, if there's no base, it's base 10. So if I do that, we can separate those out using our log properties. Remember, if it's to the exponent here, remember that sneaky one we can pull out in front. And so we have this. So it should produce a linear model, a linear pattern when we do this. So let's say that we're doing this. So again, we use powers and roots again for that rockfish, and we still expect a power model in the form of if it's a times the length cubed. Once again, here it is. Here's what it looks like. Okay, so now instead of taking and cubing the x variable, we're just going to take the log of both sides, and here's the computer printout of what we see here. Once again, we have our y-intercept here, we have our slope right here, is what we have. So again, we have all those things looking at from our computer printout here. All right, so here's the problem. Based on the output, explain why it would be reasonable to use a power model to describe the relationship. Give the equation of the least squares regression line, and then suppose again our question is, well, let's say we get something that's 36 centimeters long. How can we find the weight that we're looking for here? So again, answering the questions, scatter plot. If we did that, if we plotted that out, it's linear form, which indicates that the power model it's appropriate. The residual plot shows a fairly random scatter of points about that residual equals 0 line. So it seems reasonable that we would use that. Now, as we go to our least squares regression line, again choosing our y-intercept of negative 1.89940 and our slope of 3.04942. Now remember, we're doing the log of both variables here, so that's part of our equation that we have. All right, so if we do that, if we put in 36 and we type into our calculator negative 1.89940 plus 3.04942 times the log of 36, we get this. And again, I would wait to round to the very end. All right, now once again, here's the trick. How did we get from here to here? Well, remember, if it's the log, to undo that, what we do is we take 10 raised to this as the exponent. So we're going to go 10 to this as the exponent. That gets rid of the log part. And in which case, then solving that, we would then figure this out. We would get 702.1 grams is what we would get from our predictor using logarithms to make it linear. Okay, so it's another process, very similar. All right, now what if x and y have a relationship that can be described by an exponential? What if it's an exponential model? A times b to the x. It's not a power model, but it's an exponential model. All right, now a scatter plot of the logarithm of y against x should do that, because again, we know since we have an exponent here, we could do the log of this. Much like when this was to the second power, we could take the square root of this, or if that was a third, we take the cube root of that. What you do is just do the inverse operation to the y is what you do. And again, you can kind of see why that works. Once again, you can see how we can get that out and plot that. We'd get a linear linear pattern is what we would get there. So, all right, so once again, here we go. So here's the problem. Gordon Moore, one of the founders of Intel, processors, said that we'd be able to double every 18 months. And it's called Moore's Law, one way to measure the revolution in computing. Now, they didn't give us the data, but they do give us a little scatter plot over here of years now. 0 is 1970, so it's years since 1970. We're going to see the number of transistors, and boom, you can kind of see that explosion. It's clearly a linear type equation, and it goes all the way up to 2016. Okay. Now again, if Moore's Law is correct, then an exponential model should describe the relationship between the variables. All right, now here's the scatter plot of the natural logarithm. Remember, that's base E, where we do ln instead of just log, of the number of transistors on a computer chip versus years. So what we did is we took the log of the y variable is what we did. And as we kind of look at this, yeah, it's approximately linear. It's pretty linear, I would say. So again, that's going to make it seem reasonable that that would be the case. Okay, so here's a computer output. Now, once again, if we're doing our output here, again, constant, this is our y-intercept, here's our slope. Okay, so again, we want to make sure we're going to take the natural log. Instead of just using y, it's kind of nice to use the transistors so we know what we're talking about. And then, of course, this is the year since 1970. So again, remember, we just took the natural log of the y variable. Okay. All right. So here we go. Let's use that model. Okay. Now, once again, we're going to put, if it's 2020, that's 50 years since 1970. So we put a 50 in there. Compute what that is. Now, once again, like we did before when it was just log, we said 10 to that power we'd get rid of that. So in this case, natural log, we're going to use e to this power. So we go on your calculator and we figure out, wow. All right, we're talking almost 68 billion transistors is what we're looking at there. Okay, so another way of doing things with the log is what we can do. All right, so how do we know which one to choose? So suppose that a scatter plot shows a curved relationship between two quantitative variables x and y. Okay, how can we decide whether it's a power model or an exponential model best describes it? Well, here we go. This is a good example on what we can do here. Okay, so how is the braking distance for a car related to the amount of tread left on the tires? Researchers collected data on the braking distance, okay, that's in car lengths, for a car making a panic stop in standing water, along with the tread depth of the tires. Usually tread depth, they'll measure them as in 30 seconds of an inch. Okay, they put a little thing in there. They can get the depth. They should do that anytime you bring in an oil change or rotate your tires. They'll check your tread depth. Okay, so here's a linear regression output for 3 different models, along with a residual plot for each model. Now, model 1 is based on the original data. So, and then models 2 and 3, which we'll get to, involve this. Okay, so if we just do braking distance versus tread depth, we're seeing something like this. Okay, all right, so there it is. All right. Oops, let's see what we got here. Oopsie, let's go over here. Sorry, clicked on the wrong thing. All right, model 2. Now, this is if we take the natural log of both the braking distance and the tread depth. So again, what you're seeing here is this is the residuals, okay, residual plot. And yeah, so you see that. All right, and then next one that we take a look at will be just doing the natural. Okay, that's if it's exponential. We just do the natural log of just the braking distance. And again, as we take a look at those, so let's put those all together and let's kind of see, well, which model does the best job. Now, remember, when we do a residual plot, we want to kind of have random. We don't want any type of pattern. So again, you can see a pattern here. You can see a pattern here. This one. So model 2, this one seems to be the best model because there's no real pattern involved in that residual plot as we do it. So that would be the best one. There's no leftover curve pattern. Okay, so that's kind of why this is kind of the most appropriate model. So we would then again say that it's probably going to be a power model is what we're going to look at. So let's use the model chosen and see if we can calculate and interpret the residual for the trial when the tread depth was 3/32 of an inch and the stopping distance was 13.6 car lengths. All right, so here we go. So here's our computer printouts. So once again, we can come up with our model. This is our y-intercept. This is, again, our slope. Okay, now that we've made it linear, we can do that. So remember, it's the natural log of braking distance, which we don't know. We get 2.9034. That's the y-intercept. Here's your slope. And then our tread depth, of course, is going to be 3/32. So we're going to put a 3 in there. And we'll compute. We'll get the 2.608. Now remember, to solve, we got to go e to this power. So we have to go e to this power. That's to get the braking distance. And we get about 13.6 car lengths, 13.57, which rounds very nicely to there. So again, being able to decide which one is which is what we have. Now, once again, you always want to make sure that we answer the question, is that when the tread depth was 3/32 of an inch, the car traveled 0.03 car lengths further than the distance predicted by the model. Okay, so the model said that, and when we did the x equals the natural log of tread depth, and when y equals the natural log of braking distance. All right, so not too bad difference there. All right, so once again, what we're trying to do in this section, again, we have to use transformations involving powers, roots, logarithms to create a linear model. That allows us to use our regression models to use the model to make predictions, and then being able to tell which one transformation does a better job. And again, a lot of times it's looking at that residual plot, whichever one's most random, doesn't maintain that curve pattern, that's the one that you're going to want to use. All right, so there we go. That's going to be the end of 3.3 and the end of chapter 3. So we'll start our review process and I'll get everything going. So, all right, till next time, I'm Mr. Boone.